Why, hello, all you weird calculus people. We got some more stuff that we got to do that deals with inverses. But inverses of trigonometry functions, there's not a lot to do with this because it truly is just a memorization thing. I'm going to show you the 6 inverses. You are responsible for just simply memorizing the structure. The first thing we're going to do, though, is I am going to show you and kind of prove to you where the inverse sine function comes from, the derivative of the inverse sine, just so you see why it looks the way it does and where that stuff comes from. And then we're just going to apply the definitions. So inverse trig is all about memorization. So please look for patterns when you see the different trig functions and begin memorizing those. So I'd like to present my screen to you just to show you all of the different inverses that there are, okay? So what you should see here is you should see the different inverses. So we have the inverse sine, okay? We have inverse cosine, inverse tangent, inverse cotangent, and then inverse secant and inverse cosecant. More often than not, we use sine, cosine, and tangent, but the AP test will sometimes throw a little wrench into you and have you do a secant or something like that. So take a look at their definitions, and you will notice some very close similarities. So that's the first thing I'd like to talk to you about. There are some similarities between sine and cosine. Please note that really the only difference between the two is one of them's a positive one and one of them's a negative one, okay? Same thing holds true with tangent, okay? Notice one of them's a positive one of them's a negative one. Same thing holds true for secant and cosecant. One of them's a positive one of them's a negative one. But notice almost all of them have some things in common. There's a square root, and notice it's some combination of 1 and x squared under the square root, whether it be 1 minus x squared, 1 plus x squared, or x squared minus 1. It's all something like that. And then, of course, secant and cosecant throws in this absolute value of x. So please remember those two weird features. So those are the functions. So I do want to show you why these functions look the way they do. Okay? So let's go down to example number 4. Or number 4 down here, it says example 1, and it's just kind of proving using implicit differentiation why the inverse sine is equal to that one weird sort of function. Okay, so there's a couple of things that we're going to talk about when we do this. So let's do a quick sort of review, and actually let's kind of set this up and let's put this into a triangle just to kind of get some understanding. So what we have is we have y equals sine minus 1 of x, okay? And that's actually going to be like x over 1. So remember, when we did inverse trig in pre-calc, this means the angle. What we're trying to find is we're trying to find the angle where these two things are true. So the angle is y. So I'm going to label this y. And then we're talking about sine, so it's opposite over the hypotenuse. The opposite's going to be x, and the hypotenuse is going to be 1. So this is the first thing you need to do to understand how we go through and calculate this. So when we go through and we start to figure some things out, we need to have a few things at the ready as well. We also need to know what this side is right here if we're going to do any sort of trig stuff. So what you have to do is you have to use that Pythagorean theorem again. So we're going to use a squared plus b squared equals c squared. So remember a and b, and let's just call this the c right down here because that's the thing we don't know. So we know the hypotenuse. I'm sorry, let's call this b because we know the hypotenuse. Let's call this b. So we're going to try to figure out what b is. So we're going to replace a with x squared. We don't know what b is, and we know c is 1. Okay? So let's solve for b. So if we're going to solve for b, we need to move the x squared over to this side. So that's going to be b squared equals 1 minus x squared. And then you need to take the square root of both sides. And remember, when you take the square root, it's plus or minus both sides. But here's the thing. We are only going to use the positive because you can't have a negative side in real life. So b is going to equal the square root of 1 minus x squared. So let's draw that over here. So this is now the triangle that we're going to use. We know this is the square root of 1 minus x squared. We remember this is x, this was y, and this was 1. Okay, so here's what we're going to do. We're going to start with our original equation, and we're going to convert it back to a sine function. So if we have inverse sine here, to kind of go back, we're going to end up with the sine of y equals x. So now, what we're going to do is we're going to use implicit differentiation because we know we can take the derivative of that. Okay? We can take the derivative of sine of y. We couldn't take the derivative of this yet because that's what we're trying to prove. So we're just going to convert it back to its original equation where sine of y equals x. So now, take the derivative of sine of y. Okay? So the derivative of sine of y is cosine of y times y prime. Because remember, it's implicit differentiation. And then the sine of x is 1. Okay? Now, we want to get y prime by itself. So we need to divide by the cosine of y. So y prime is equal to 1 over the cosine of y. Now, we can't have a y in there. We need it to be in terms of x. So that's kind of where we have to go back to this triangle that we drew. If you think about it, let's go with this. The cosine of y is equal to the adjacent over the hypotenuse. So it's going to be the square root of 1 minus x squared over 1. So what can I replace the cosine of y with? I can replace the cosine of y with 1 minus the square root of, or the square root of 1 minus x squared. So y, the derivative dy dx of that function is going to be 1 over the square root of 1 minus x squared. And that's our sine function. So when you have inverse sine, this is why the derivative of inverse sine looks the way that it does. Okay? So you are not going to need to know how to prove all of these things. I just wanted to show you this in order for you to understand why they look the way that they do. Why do each of these trig functions, inverse trig functions, why do their derivatives look like this? Okay? And when you see how you have to prove it, you can kind of see where those derivatives come from. So you do this same sort of thing with all of them up here.